Hi everyone, my name is Zongliang Yue from the Informatics Institute in School of Medicine at the University of Alabama at Birmingham. My mentor is Dr. Jake Chen. Here is his email. Today we're going to introduce the DEMA, a distance-bounded energy field minimization algorithm to model and lay out biomolecular networks with quantitative features. We're going to introduce the basics in graph layout algorithms and a distance-bounded energy field minimization algorithm in the background. In the method section, we are going to introduce parameterized energy model, solution for it, heuristic star, and evaluation matrices. In the end, we're going to conclude our work. In biology, graph layout algorithm can review comprehensive biological context by visually positioning graph nodes in their relevant neighborhoods. We are motivated by the automated graph layouts and intend to present insightful knowledge in the layout generation. Our aim is to develop a powerful layout engine that arranges items automatically and meaningfully so that you can quickly spot patterns. The gene patterns can be derived from functional genomics analytics and will be useful in combining the network visualization tools such as gene terrain. Gene terrain is a 3D visual technique to discover the signal in a continuous metric in space, and it can effectively reveal several types of molecular biomarkers which are traditionally difficult to detect due to noises in data. The gap for such visual exploration is whether we can provide a grid layout. The challenge is that current layout engines normally do not consider node, edge, and node site properties. Especially the missing knowledge of enriched pathway can be a big issue in the layout generation. Therefore, we developed the distance-bounded energy field minimization algorithm, also called DEMA, to natively consider various biological factors to enhance the interpretation of the complex network graphs. The four properties listed here are the common critical biological factors we're going to model in the DEMA layout. First, the topological property. DEMA will going to show some modularity so that the hub genes do not overlap each other. And this property can be formulated in the repulsion energy. Second, the node weight property. Two interacted genes will become close if they both have a high forward change regarded as a positive association. Edge weight property. If the interaction between two genes is strong, denoted in the thick edge, or positive correlation between the two nodes denoted at the red edge, then those two nodes will become closer. Those two properties can be reflected in attraction energy. Fourth, the grouping property. Functional genomics analysis can provide enriched pathways or functional groups in the network. As you may be familiar with many layout tools listed here, we have organic layout, OL, First Atlas 2, FA2, Frontman and Real Gold, FR layout, Force Directed layout, Edge-weighted force directed layout, EMAP layout. In the comparison, DEMA has considered all the four properties at the same time. In the parameterized energy model, we formulate the three energies mentioned before. In this grand energy function, we have EA, EB, EC denoted as repulsion energy, attraction energy, and grouping energy. We also have Ka, Kb, Kc to control this coefficient. Kb versus Ka measures the balance between repulsion and attraction. When it becomes larger, the attraction influence is strong enough to pull the node together. Kc controls grouping. When it becomes larger, the genes in the same group tend to fill in a smaller space. Jump to a detailed view of the energy formula. We have three energies in the modeling. In the repulsion energy, we adapt the topological factor Ri, the RP score of node I. The original RP score is proposed in the literature published below to indicate the topological importance. If the node edge or node weight become large, we need to increase the distance between the node to maintain a smaller repulsion energy. In the attraction energy, we introduce the force change as a numerator and the constraint weight Wij as a denominator to formulate the attraction. To provide a reasonable range of distance, we define the lower bound and upper bound. Lower bound, capital Dij, is an extremely small constant. We set 10 power by -8 in default, which makes sure any two nodes do not collapse. In the upper bound constraint weight, we have interaction coefficient and the effective coefficient. The interaction coefficient can be measured by the reliability of the edge using in the protein-protein interaction network using the static model, such as the PPI score in the database, HAPPY database we mentioned below. The effect coefficient is defined as a measure to evaluate the correlation between genes based on the gene expression, such as the G-card index or Pearson correlation coefficient. When IC becomes strong, that approximate to 1, or EC is positive, that approximate to 1, the constraint weight will be extremely small, and the attraction energy can be reduced when the real distance is approaching to the constraint weight. In the grouping energy, we use DIC to indicate the distance between the annotated genes and the gene set center C, and we expect this distance to be small in reducing the grouping energy. We use the stacked force derived from the derivation of the energy function to minimize this energy function. The stacked force of node I composes three forces. Fija is a repulsion force exerted by node J using the blue formula. It can become exponential decline while the distance increases. Fijb is the attraction force exerted by node J using the red formula here. It will become exponential growth while the distance between I and J increases. Fic is a grouping force exerted by the center of the groups using the yellow formula. There is a linear relationship between the grouping force and the distance, and the direction is from the node I to the group center. To find the local optimal solution iteratively, we apply EMA algorithm. So that DEMA delivers a suboptimal solution to a global problem, and the local field energy needs to be minimized using the stacked forces to continue the search beyond the local optimization. To further convert the energy function to a minimum fast, a heuristic style is proposed. First, we construct the initial network and find optimal distance to minimize the energy system using the derivation of the energy function. After we define the optimal distance between any pair of nodes, the formulation is transformed into the Kamada-Kawai model, KK model, and we can solve it according to the stress majorization algorithm. In the performance evaluation, we introduce space filling to evaluate the visual clarity, hub shrinking to evaluate the structure modularity, and the inside the mean value of the square distance, IMSD, to evaluate the grouping performance. First, we normalize the nodes coordinates at 0 to 1 for each axis. In measuring SF, we build the matrix and see what percent of the small squares are occupied by the nodes. The larger it is, the more dispersed the nodes are. HS measures the arithmetic mean of the square distance between each pair of nodes that share an edge, such as the distance between the two dark nodes. Obviously, the smaller the HS value is, the more nodes shrinks. The overall modularity is measured by the HS divided by SF. The smaller this ratio is, the better it is. IMSD is defined as the mean value of the square distance between any two genes in the set divided by the mean value of the pairwise square distance among all the input genes. Such as the nodes in the blue color indicate they are annotated under the same group, we expect the distance among them to be small. Next, we develop a plugin to the Cytoscape software to generate the DEMA layout. In the base model shown as the part A, by giving the edge information only, DEMA can generate a layout with topological modularity. In part B, the edge file includes two computational biological factors, SE and EC. With additional edge-weighted property, DEMA will highlight those edges attributes by providing a large variation of the edge lengths. In part C, the node file includes a for change. With for change, DEMA would not only show the network modularity, but also reflect the relation between the nodes by collaborating the length of the edges. In part D, the nodes file include gene sites annotation, and by importing that, the layout can show the grouping ability. We compare DEMA with other layouts using a random network with 100 nodes satisfying scale-free property. The 2A to D are generated by DEMA with different values, the parameter KB versus KA. We can see that when KB versus KA become large, the modularity becomes more obvious. However, when the distance between the surrounding nodes and the hubs becomes small, it's difficult to observe the surrounding nodes, which means it loses clarity. Compared with the other layout shown in the graph E to H, we can see that the subgraph E roughly corresponds to A. The issue here is the hubs in the layouts are not obvious in both. F roughly corresponding to D. The issue in F is there is no hierarchy structure in the hub and its neighbors. G roughly corresponds to C. The issue is that edge cross in the subgraph G. H roughly corresponding to D. The issue is a lack of the clarity. We found the subgraph C delivers the best layout in a balance between the modularity and clarity. We also quantitatively confirmed our discovery using the hub shrinking versus the space filling, and here DEMA provides the best performance here. To maximize the modularity performance, we control ratio of KB and KA using different number of nodes. Subgraph A and B show the space filling trend and hub shrinking trend in corresponding to the ratio. In subgraph C, we can see the best parameter for the smallest ratio is usually close to the number of the nodes. Particularly in the subgraph D, we can observe that given 100 nodes with different number of the edges here, the best parameter for the smallest HS-SF ratio is still close to the number of the nodes. Therefore, the default value of this ratio should be the number of the node. We control KC to review gene grouping as shown in figure 4. The genes in the set will become closer as KC increases. Next, we report the performance using IMSD and space filling with subgrouping size varies from 5%, 10%, 25%, and 50% of the total nodes. We have the 100 nodes in the first row. We can see that IMSD becomes smaller as KC increases, which shows that the nodes in the group become closer. From this subgraph B, we can see that space filling is almost the same before the KC is equal to 30,000, which is the 300 times of the node size. When KC is larger than this number, space filling declines rapidly, which means there are some nodes are overlapped. We repeat the process by using 10 random network with 500 nodes. The results are still the same. Therefore, the default KC value should be defined as 300 times the number of the nodes to balance between to a balance between the visual clarity and the grouping degree. We applied DEMA in a real case study in autism spectral disorder ASD. Autism is a complex disease and it is still difficult to determine its etiology. Here we want to characterize genes that hasn't been annotated by genomics information before, but are essentially in the physical connection to the hub genes that well studied before. We adapt the ASD model in the previous published work and focus on the module number 13 reported in their paper, which includes 199 genes. In this module, there are two annotated genes, Safari reference genes, and de novo copy number variance genes, annotated in the red color and blue color. DEMA performed the best in both Safari and de novo gene grouping reported by the IMSD score. There are three candidate genes, DLG2, DLG3, and DLGAP1, denoted by the red arrows and highlighted in the connection to the hub genes in the center of the graph. These three genes are considered to be new candidates related to autism with literature support. In the Alzheimer's disease application, we want to highlight genes that involve in multiple pathways and make the pattern clearly. The input is 680 candidate genes in view of the genetic risk collected from the ALZ gene database listed below. After processing with the gene set enrichment analysis using PagerDuty database, we found 6 highly relevant pathways, are able to find those genes shared in multiple pathways easily in DEMA compared to the organic layout. For instance, Apple A1, Apple B, LDLR, Apple E, and ABCA1 involved in at least 4 pathways here. The remarks of DEMA come to the 2 major points. DEMA firstly introduced a parameterized energy model to integrate the critical biological factors. Particularly since DEMA adapts energy-based algorithm, the second-place algorithm, organic layout, is able to achieve the similar performance to the DEMA-based model using an unweighted network. However, given the biologically functional annotations, DEMA makes a big difference by reviewing biological groupings and those surrounding candidates intuitively. DEMA also outperforms many traditional layout algorithms. We comprehensively evaluate the performance using space filling, hub shrinking, and inset mean value of the square distance. We expect DEMA to be a major tool in network analytics. I'd like to thank the contribution from AI.med lab at University of Alabama and the JUICE lab at Peking University. Here is a code repository and website. Thank you for your attention.